So, Unit 4, Momentum. An object at rest remains at rest, and an object in motion remains in motion. You probably remember this from Unit 2. Momentum is usually symbolized in P, and this is usually signifying linear momentum. When we say momentum, we usually talk about linear momentum. When we want to say something else momentum, like rotational momentum, we say something else. So, it shows the tendency of an object to remain in motion. This is pretty intuitive because you multiply the mass with the velocity signifying the motion, the mass signifying the object. So in this chapter, unit, we're going to talk about two different scenarios. Collisions are scenarios in which the forces between the objects greatly exceed the net external force of the object/system. Explosions are scenarios when forces internal to the system move objects in the system apart. So what's important in these two scenarios is that when we analyze them, we only look at the final and initial status of the system. This is because momentum is a vector, so it has direction, therefore you can just look at the initial and final state. So impulse is also kind of important. The change in momentum is impulse. So momentum is mass multiplied by velocity. If we divide that by time, we would get mass multiplied by velocity over time. Therefore, you would get force, which is obvious because you dividing velocity by time would get acceleration, and acceleration multiplied by mass is force. So impulse, as we said, is change in momentum, and how we get impulse is pretty weird. So we integrate force. And since we know that force is basically dp over dt, momentum over time, we can get the change in momentum by setting a certain time interval like that. The impulse is just integrated force in respect to time, which is change in momentum. Pretty simple. And because of that relationship, we can also draw these like graphically. So force in respect to time, the area under that is impulse or slash change in momentum. Momentum in respect to time, you can get the slope as the force because momentum over time is equal to force because acceleration and everything. And this is a pretty similar relationship between acceleration in time and velocity in time. So acceleration time being adjacent to force time, and velocity time being adjacent to momentum and time. The only difference is that mass is taken into play when we're talking about momentum and impulse. But that doesn't really matter because mass is technically a constant in most scenarios. So what's cool about momentum is that a system of objects can be described as one system with one velocity. You probably remember that from Unit 2. As I said, Unit 2 is super important. It's going to be related to literally every unit. So basically how you think about this is you get tiny, tiny masses with all of their little velocities, and you multiply them together, and you get all these different momentums, and then you divide it by the entire mass, and you would get the average velocity of all these different point masses. That is the entire center of mass velocity. That is the velocity of that object. When it is a scenario in which there is no net external force given to that system. So that leads to the conservation of momentum. Any change to the momentum of an object within a system must be balanced out by the opposite change in momentum elsewhere in the system. So you can also think of this as the idea of point masses and their velocities. So whenever there's a point mass change in there must be a point mass change in somewhere else in opposite direction. Not mass change, velocity of the point masses. So this includes collisions, both elastic and inelastic, because in both scenarios, we think of the momentum as being conserved. So elastic collisions, both momentum and kinetic energy is conserved. In inelastic collisions, momentum only is conserved. Their kinetic energy is usually lost through non-conservative work, such as drag force or probably heat most of the time. So these are the two different types of collisions, the elastic collisions and the inelastic collisions. So as you can see, there's a diagram, mass A, mass V, their velocities initially, and their final velocities, which is signified through the prime. And what's interesting is that because kinetic energy is conserved, the velocity of A plus velocity of A prime has to equal velocity of B plus velocity of B prime. The reason why is because of the kinetic energy equation. you can put that here and then that here, and then you will get the equation that velocity A plus velocity A prime equals to velocity B plus velocity V prime. So for inelastic collisions, it's a little weird because now the kinetic energy is not conserved and you can't use this little shortcut. So mass of A multiplied by velocity of A, blah, 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 the same thing as the elastic one. But this one is weird because inelastic collisions, they usually stick together. Most of the time in real life, there's no perfectly inelastic or perfectly elastic collisions. But in this scenario, we're only talking about perfectly inelastic collisions. Everything in real life is slightly inelastic. Sometimes, most of the times, they bounce back. But in here, we all stick together. So they're quite easy to get. So you just divide the initial momentum by the combined masses, and then you would get the final velocity. So some/all of the initial kinetic energy is lost as heat or other forms of energy. Yeah, so that's how perfect inelastic collision works. The final thing that I want to talk about is when two objects of equal mass collide. For elastic collisions, the objects exchange velocities. For inelastic collisions, the object have the final velocity of VA plus VB. They just add them together because they're of same mass. So that's how it is. So there's equations. Obviously, the equation for getting the momentum, the force equation that you use to get impulse, and then the integration version of that, and then getting the center mass velocity equation. So that's unit 4.